Morning, everybody. My name is Nicola Cairo. I am project officer at ETN Global, and today we are having a webinar on Finno Exergy's PGC technology. The CTO of Finno Exergy, Fabio Ciccateri, is here today to present the potential of this technology in terms of fuel flexibility and efficiency improvement in gas turbine. Fabio will explain the potential of this specific technology when it comes to permitting gas turbines to operate with any mixture of methane and also hydrogen. So with this, I'd like to give the floor to Fabio for his presentation, which will be then followed by a question and answers with the presenter. Thank you very much. Fabio, the floor is yours.
Thank you, Nicola, for the introduction, and thank you, everybody. Good morning. Thank you to have joined this webinar. It's my pleasure today to try to give you an overview of what we are doing at Finno, why, and what are the long-term perspective for this interesting technology. So if it's fine for you, I will start to go through the presentation. So I would like to start by trying to address the reason why Finno exists. If you have a look at gas turbines efficiency across the last decades, the approach has been very much an incremental one. And we are reaching, for basic thermodynamic reasons, a limit for gas turbine efficiency. And that's due to reaching higher and higher pressure and temperature and mechanical limitation for materials. And if you do an analysis of where are the losses in modern gas turbines, you will see that most of what is still available it's in the combustion system. So turbines and compressor have been optimized almost to the limit, but there is still a lot of room for improvement in the combustion process. And that's basically due to the nature of the combustion process. So the constant pressure way of burning fuel is not the most efficient way to convert the fuel energy into mechanical power for basic thermodynamic reasons. So because of this, there is all of a research topic called pressure gain combustion that it's studying different ways to replace the constant pressure combustion process with a constant volume, so a pressure increasing combustion process that will reduce the entropy generating during the combustion process and open up ways for a step change in gas turbines efficiency. We at Finno have chosen as approach the one of having a periodic combustion process. To make it simple, with the same thinking about having same compressor pressure ratio and heat input, we will gain a higher pressure inlet at the turbine. With this higher pressure, we can extract more power for the same amount of fuel burn, and this results in higher efficiency. We have done some in-house simulation to try to estimate what could be the relative efficiency improvement for different kinds of gas turbines. And it looks like that the biggest gain is for lower compression ratio machines, and it asymptotically tends to reach a 10% efficiency improvement for the higher pressure ratio application. So we are talking about a big change, but also a big benefit out of this this new combustion process. So I'd like to frame you a bit what is out there in pressure gain combustion. So there is two main differentiation between the technology, a detonation-based approach and a deflagration-based approach. Most of the research in nowadays is done in a rotating detonation engine, a lot in US. That is this detonation-based combustion process where you have detonation front propagating into a circular chamber, and the gain in pressure comes from this detonation combustion process. We at Finno have chosen to use a more gentile process that is a deflagration combustion type. Pretty much what happens in your internal combustion engine under your car. So a lot of the know-how and of the physics comes from the piston engine world. And the process, the basic thermodynamic process, it's well understood. The combustion phenomena are well understood. And while for the detonation application, there is still a lot of research done to understand really what happens during the combustion process in the detonation front. So that said, I would like to explain you synthetically how the system works. So on the right, you have a schematic representation of what is the combustion chamber, very schematic. You have basically what could be a thing of a piston with a set of valves on the inlet. So the valves are facing only, let's call it cold flow. So what is coming from the compressor, while the section that is facing the turbine, so the bottom part, is constantly open. And on the left, you see a plot of one cycle. So as I said, this is a periodic operation. So this happens in a cyclic way. And you can see here the combustor pressure ratio and the temperature ratio inside the chamber during one cycle. So the cycle starts with the chamber being scavenged. So we have the chamber that is full of exhaust gases from the previous cycle. We open the inlet valves, we scavenge the system, we introduce new fresh air, mix it with fuel, and then we have a controlled ignition process that starts the combustion. Due to the fluid dynamic condition that we have in the chamber, so we have an high turbulent regime inside the chamber that enhances flame front propagation. So we are able to have a very fast combustion process happening in the chamber. And this results, even if it's not a fully properly constant volume combustion, but the flame propagation front is higher than the expansion ratio of the gases. So this results in a sharp increase in pressure and temperature inside the chamber. So in the meanwhile, we have closed the inlet valve, the pressure and temperature goes up, the gas starts to expand downstream to the turbine. And when the pressure inside the chamber is lower than the inlet pressure, we start the cycle again. And this happens around 10 to 30 times per second. So 10 to 30 times, 10 to 30 Hertz is the frequency of operation of the system. This is how we started. So back in 2017, we decided to prove that our ideas could work in a proof of concept test unit. So where we put together a small scale closed system composed by two turbo machines taken from the automotive world, so two radial turbocharger connected to this twin combustor. The idea was to show that the system could work in a closed loop operation, could generate the required power to power the compressor, and there would have been an additional power to be dissipated by this adjustable valve that was there basically to simulate the presence of a power turbine. And the goal was to focus on measuring pressure and temperature before and after the chamber to show that we could generate the amount of pressure gain that we were hoping to get from our early simulations. The system worked pretty well, reliably. We were able to start the combustion process, go up in in temperature and pressure, then keep the system steady and measure the performance of the system. We have reported it in a paper published in 2020. You can have access to it from the link that is in this slide. And the results show that we were basically able to gain almost 28% of pressure. So we had 4.5 bar at the inlet of the combustor, and we measured 5.75 bar at the turbine inlet. So this base of this amount of pressure gain will enable us to reach a considerable amount of efficiency gain that is not proportional, but it's related to it. The system was also very fuel flexible, so this was running with liquid fuels. So we were able to run this system with a lot of different kind of liquid fuels, from bioethanol with up to 20% of water content, methanol, gasoline, Jet A, Everfuels, kerosene, blends of them with the same hardware, just basically changing the fuel line. And we started to think that this could be working very well also with hydrogen. In general, pressure gain combustion technology, they are tested with hydrogen because hydrogen is very reactive fuel. And the faster you burn, the higher is the pressure that you can actually generate. With that in mind, we took part to a startup competition arranged by Shell and other partners in 2020, and we won. That year was based on hydrogen technology, so we won that competition, and we started to work with Shell from 2020. First, as winner of the New Energy Challenge, we went to upgrade what was the test unit proof of concept prototype. So the idea was to add the third turbine stage there to actually measure extract power, measure efficiency, and compare it with what would be an ideal gas turbine, because unfortunately there wasn't any real gas turbine, micro turbine working with that system, that exact same system. So the first, when we tried to measure efficiency, adding a third turbocharger stage, the result were we could barely notice any difference, and there was a lot of losses. The system was not designed to operate efficiently, so there was a lot of thermal losses, fluid dynamic losses. But by optimizing the system, we showed the potential to gain up to a 40%, almost 40% efficiency gain for that small system. So an equivalent system operating at the same pressure ratio, compressor pressure ratio, and turbine inlet temperature. So the potential is high, and we decided with Shell to move forward with another project inside the Shell Game Changer, a slightly longer project where we intended to redesign our combustor, put in practice a couple of optimized features that we had done through the years, and convert it for a gaseous combustion, and prove that the system could run with any mixture of hydrogen and methane, and in parallel develop a technology development roadmap for retrofitting industrial gas turbine out there. So the overall objective was to start to de-risk this, show what is the beachhead market for the technology, and convince the OEMs that this is something worth to invest in and to research further. So the test rig was simplified, so we got rid of the radial turbo machines that were a bit difficult to run in a repeatable way. So if you wanted to change pressure ratio, you needed to change turbo machines, and it was a bit complicated. So we removed them, and we added an external compressor and an air reader to give the inlet conditions to the combustor that we wanted. So the right pressure ratio and temperature inlet. And then we added this. We did a new design of the combustion chamber, and we added this section here highlighted in red. Basically a new hot section simulating the presence of a gas turbine. So a combination of an heat exchanger and a back pressure valve to simulate different size gas turbine. So we were also able to test how the combustor reacts with bigger or smaller gas turbine attached to it. And we developed a new fuel line to be able to inject gaseous fuel, and specifically hydrogen and methane. So the injection system, I'm not going to go into the detail, but just to make you understand, we are doing injection in two strategic points with two different fuel. So it's kind of partially premixed and partially direct injection concept, where we can change the amount of hydrogen or methane by adjusting the duration of the injection. So this is a periodic thing. So we have one additional variable that it's time, that you usually don't have in gas turbines. So that's how, in principle, it's controlled. I have a video. Sorry, I forgot to share the audio. Nicola will put this back on.
Sure, Fabio. Do you need some help for sharing?
No, it's okay. Just let me know if it works, the audio. So before starting, you will see an optical axis here where you can see the combustion process and the exhaust pipes that are feeding what is the turbine simulator. They will start to glow red because we have around 950 Celsius on the exhaust in this particular test. So this is the measuring station before turbine, where we are measuring all kind of physical properties before turbine, and before there is another one similar on the cold side before the combustion chamber. And this is a summary of the results. So we did pretty extensive testing with different kind of air mass flow and fuel blends, and it's basically with all of the condition we are able to run the system steadily, achieve over 30% of pressure gain. So this is the amount of the difference between the pressure in the inlet and in the outlet of the combustor. And so on this left plot, you see this average pressure gain compared to the combustor temperature ratio. So the combustor temperature ratio gives you an idea of how much fuel we are burning. And you see that with the points at 100% hydrogen, we had slightly lower performance. And that's because we were forced to reduce a bit of the fuel power because of the ignition issue. So what happened is that the hydrogen is so reactive that if there is some hot spot in the chamber, it starts to burn. So we actually notice it when during the test, by mistake, the plug went off and the combustor didn't stop. So it was running continuously, and it was actually running really steadily. So we have identified the issue. So basically what happens is that if you inject the fuel and you start to burn when you are not done with injecting all the fuel, part of it will burn in a constant volume way, and part of it will burn in a constant pressure way. So we have overcome it, and we have now implemented a new fuel system specifically for this purpose. So we are able to inject more fuel in a shorter time, and in that way we can overcome this issue. So we are expecting that in the next test campaign that will start in January, all this point will move with the clouds here on top. So this is still quite small prototype. We have run maximum around 120 grams per second with this, and the fuel power is around 100 kilowatt. So we did a simulation to estimate how much work, how much efficiency we can expect by calculating the enthalpy content of the gases at turbine inlet, so the station that I showed before, and thinking of extracting that amount of work with some turbine efficiency that in this case has been chosen the same as Brayton cycle, and showing an efficiency gain of 20% that is in line with what we have been testing. This was run at 12 bar pressure inlet, so similar to what is an industrial gas turbine pressure ratio. And even assuming lower turbine efficiency, we still get considerable efficiency gain from this. In parallel to this experimental work, we have done a market study in collaboration with the Fraser-Nash consultancy to identify what would be the beachhead market for this application. So as I showed before, there is some particular gas turbines where we can expect higher efficiency gain. And it turns out that the best fit for this for entry market will be facility power generation over 0.5 megawatts, so something very common in oil and gas and other kind of industrial process. Also marine is interesting, but due to the size, the idea is to go first in industrial gas turbine. To prove it in gas turbines between 3 to 20 megawatt to start with, and then expand to different kind of markets. We have also identified what are the risks related to this. So of course, the big change that we are doing is we are introducing a pulsating flow into a machine that has been designed for steady state operation. So it's clear that mechanical vibration and axial loading are the main challenge that we need to overcome, and that's why we are working on it already. We are actually on the process of designing specifically developed stator to place in front of the to be implemented so that it can smoothen out the pulsating amplitude of the flow. So reduce a bit of pressure gain, but make it much easier for the gas turbine to digest the flow. We are doing this in collaboration with Pardue University that has been designing and developing this kind of components for the leading detonation engine. And there is all sort of other kind of things that needs to be sorted out, and that's why the next step it's really gonna be the integration phase. So the combustor by itself, we feel that we have a grip of it. We know how the system works, how to run it smoothly. Now it's time to integrate it to an actual gas turbine. And the idea is to have a demonstrator in place where we show that the system runs efficiently and reliably, and it's fuel flexible so that we can run with any blend of hydrogen and methane. We are starting this project next year, in collaboration with Shell and other partners. And the goal is to select one industrial gas turbine and retrofit it with our system and build 1D models and 3D models of the system, specifically on rotor dynamics and fluid dynamics model, to estimate what is the mechanical effect on the gas turbine engine, what is the efficiency that we can expect with a much more detailed simulation that takes into account all the losses that the pulsating flow will introduce in the system, and also have an estimation of the cost of the retrofit. So the idea is to really have a clear picture of what is the potential of this before moving into a piloting phase. So we are looking for additional partners between OEMs, research center, and university that think that their know-how could be valuable and they are interested in this. So please reach out if you are interested in the collaboration. So the long-term plan it's something like this. So next year we are focusing. We will do the simulation of it, identify, do a preliminary design on how to do the retrofit, the upgrade. Let's call it as we want. And then test in the lab, in lab condition, the singular component required, and then move into a gas turbine demonstrator by 26, 27, and enter the market after that. If you have any questions, I'll be really happy to take them. Thank you for your attention.
So thank you very much, Fabio, for your detailed presentation. Very interesting presentations. So I propose we can switch to the question and answers session. So I believe the presentation you gave today, Fabio, was added value, and we already have 3 questions by the audience.
Okay.
So I see in order we have Abhishek. So please, Abhishek, the floor is yours. Before asking your question, please identify yourself and then please move on. Thank you.
Yeah, sure, Nicolo. Thank you very much. I am Abhishek Dubey. I am doing my PhD on the pressure gain combustion topic at the University of Genoa in Italy. And the presentation is actually very good. The work was pretty interesting, and it's very much relevant to my activities that I'm doing on the theoretical level. My question is about the decrease in efficiency of the turbine with the pulsating outflow. How much decrement you actually observed, and if you were able to quantify that, because in one of the slides you mentioned the same efficiency for the turbine, for the Brayton cycle and the PGC. So how much was the efficiency drop?
The efficiency drop that we didn't measure it with the current setup, because there is an actual turbine attached to it, so there is a choke and heat exchanger. With the previous test unit, we measured it, and they were a couple of points lower than the original one. But we are talking about turbocharger that are meant to operate in with some tolerance for pulsating flow. So that's why I didn't mention it before. So we had the original efficiency of the turbocharger was 67%, and we measured 65%. So, but now the study that we're doing in collaboration with Purdue, it's a full CFD study on an axial machine fed with this kind of flow. And also that's where the stator design will be optimized. And after that, we will have the first, at least in simulation, numbers on what is the efficiency gain, the turbine efficiency drop that you can expect with this kind of flow. 1 second, I should have backup slide here. Yeah, so we did some basic simulation study. This was done a few years ago on a bigger turbo machine. So this is an heavy duty machine, very large machines, to try to understand how the efficiency drop on the gas turbine, on the isentropic drop, would affect the overall engine efficiency. And we did some assumption considering different degrees of impact for different stages. So what we see also on what we saw also on the proof of concept prototype was that the amplitude of the pulse, it was like 50% smaller in the second stage and like 90% smaller on the third stage. So the idea is that the first stage will be affected more, and then the other stages will be affected less. And considering this, even with a drop of 15% of turbine efficiency, that is a massive degrees, we still have over 5% efficiency gain to be reached. So we are talking about a pretty big saving we are dropping a lot of entropy generating during the combustion process. That's why we have room, even accounting for some efficiency drop on turbine, to still have a considerable gain. I hope this
thank you very much. Yes, absolutely.
Thank you very much.
Nice to know you. Nice to meet you.
Thank you very much, Abhishek. Thank you, Fabio. Then we have Simone from Politecnico di Torino, if not mistaken, right?
Yeah.
So Simone, the floor is yours. And actually, welcome to the ETN network as you are a new member.
Thank you very much. Thank you very much. It's my pleasure. And actually, my question is quite similar to the one of Abhishek. It's about the turbine module. Of course, 88% seems to be a very high efficiency if you don't redesign it, but you're saying that you're going to redesign at least the high pressure turbine stage so that you may save some efficiency points. But my question is also about the reliability of the system, because you are mentioning that you want to work in the retrofitting area, and you don't have so much room to redesign a turbine. And also there may be problems with high cycle fatigue or thermal fatigue, because you have, I don't know if you measure the fluctuations in temperature and pressure, because probably you are able to reach a good efficiency of the machine, but there not be a a good reliability of the machine due to the high fluctuations in temperature. So probably not only the turbine has to be redesigned, it has to be completely redesigned. Also the cooling system, the materials and so on. It seems to be a very big work for an entry into operation in 2027.
Maybe we are a bit optimistic on the entry level, but I mean, if you start already targeting a really late entry, then you will end up postponing it. But
No, I totally agree.
I wouldn't call it a retrofit. It's more an upgrade. You know, it's more than just switching combustion chamber. That's clear. So there needs to be a partial redesign of the system to couple this, and that's kind of it was a given for my side. Maybe it shouldn't have been a given, but it's good that you specified for what. But we think that probably it's enough to redesign the first stage partially, mostly the starter, because the new starter will do a lot of work in smoothing out the pulses. So it basically is going to convert part of the pressure in velocity and back, so that the load, the pulsating load, it's less heavy on the rotor. But this we are gonna probably publish the result of this work next year with part due. So we can, when the results are public, we can dig into it. And about the fatigue, the mechanical stress. About the thermal, what we see in the prototype is that basically the metal doesn't have time to follow the transient profile of the gas temperature. So it's happening so fast that it will reach a steady state, and it basically it's the mass average temperature of the exhaust gases. So there is a phase of the cycle where the metal is exchanging it, so it's cooling down and it's warming up, but the temperature actually doesn't go up and down because the phenomena is quite fast. So the inertia of the metal helps in keeping their temperature on the same level when we have a steady operation. It's not steady, but we are at the same working point. That's at least what we see on with the measurement that we can. So we are not measuring at a million of bars, but with the fluctuation that we see now in the gas, that doesn't follow the metal.
So that's the point. It depends on the fluctuation that comes from the combustor. We did some simulations with fluctuations from a rotating detonation combustor, and we saw that also the second rotor had a big fluctuation in load. We used an aero engine design, but the fluctuations in the second rotor were quite huge, but also the fluctuations from the combustor were quite high. So it depends mostly on what arrives to the inlet of the gas turbine. Yeah. Probably in your case, fluctuations have a high frequency, but have a small amplitude. I didn't see if you showed that because I had to leave for a couple of minutes, but I don't know if you showed the signal of the boundary conditions at the entrance of the turbine, but you may have them in your backup slides.
Yes, there was. So this is a bit, this is only the pressure. It's a bit more extensive. It gives you also an idea of what is the pressure amplitude with different fuel blends going from methane to hydrogen. But we are talking about something ratio of 2.5 between what is the pressure inlet and the peak. And the temperature goes accordingly to that. So it is a much more gentle pulse than what is a rotating detonation engine, because we don't have detonation. We don't have the shock wave coming through the system. So it's much easier to digest for the turbine. Like they are radial machines, small turbocharger, but we have been operating them for around 600 hours with any problem. There was no mechanical problem with it, and they were facing just this raw flow, so no mitigation. So what was coming through the chamber was fed to the turbine.
Okay. Thank you very much for your very interesting information. Thank you.
Thank you for your time.
Thank you, Simone. We have Jens from BASF. So please, Jens, good morning. Floor is yours.
Yes, good morning. Hi. I have two questions. Question number one is, will you also perform some mechanical calculations regarding high cycle fatigue and all stuff like that when you have chosen your first implementation of an axial turbine? And second question is, which level of emissions do you expect from your combustion system?
Yes, thank you. Thank you, Jens. Really good questions. For the first one, yes, we intend to, once the gas turbine has been selected, to develop a full rotor dynamic model on it and try to address as much as we can in terms of mechanical stress, vibrational issue, torsion loading, whatever we can with the models, and possibly, if the best case scenario would be that we could back it up also with some at least cold flow testing on the same gas turbine to validate the basic models. So it's really what we intend to do next. Try to solve, give as many answers as we can by models to the mechanical integrity of the system, because it's the next step, next confidence step that we need to gain to move into piloting phase. And for about the emissions, so the combustion, it's very complete. So we have measured a really low level of CO even when operating with 100% methane in the order of 1-digit ppm. And for NOx, we are now developing a new measuring system to measure the NOx, because this is a periodic combustion. So you basically the exhaust gas composition will vary during the cycle. So you have part of the cycle where you have a lot of exhaust gases, and then you have part of the cycle where you have basically clean air. So you need to sample the gases, mix them in a control volume, and then measure the emission of that to have an average value of what's coming out, to compare it with what is additional gas turbine emission. Our idea is that we will be much more close to what is gas turbines emission than what is piston engine emission, in the order of double-digit emission level for NOx. Also, because this we go a bit into patent area. I hope that Timo doesn't get too angry, but the basic design of the system, it's something that is similar to dual zone combustion process. So the combustion happens the first part of the combustion happens in an area that is all stoichiometric, so there's more fuel than what we can actually burn. And then there is a second area of the chamber where there is an excess air. So the combustion is completed at a much lower temperature with the abundance of oxygen. So that's also a way to, first thing, ensure that the combustion is complete, but also control NOx. But also this will be published probably next year with the result of the last days campaign.
Thank you.
Thank you for the question.
Thank you, Jens. Quintan, please introduce yourself and go ahead with the question. Thank you.
Yeah, good day, Nicolo, and hi, Fabio. Nice to talk again.
Hi, Quentin. Nice to talk to you.
How are you doing?
Good, how are you?
So my name is Quentin Michalski, and I'm a research fellow at the Royal Melbourne University of Technology in Australia. And I've worked, a bit of background on me, I've worked on pressure gun combustion at P Prime Institute, and I developed a combustion chamber to try and look at the fundamental aspects of it. And so I've got a couple of questions for you, Fabio. Things you didn't talk about. I mean, you talk a bit about, I have two questions. The first one is about the emissions, but it's not about the suit. And the second one is about the wall temperature. So to go with the first one, so you're saying the suit is low, fair enough. So that's what you measured. I'm just wondering how much, like, are you guys had a look at the unburned gas, or like the feasibility of measuring the unburned gas? Because
we are burning CO.
We are burning CO. You're burning
as a marker. We are measuring
All
CO,
right.
so that's the marker for the complete combustion, and it's really low. It's in the single digit level.
So
ppm.
you did some sort of measurement at the exhaust with like
Yes,
some sort of
with
fair enough.
with the automotive type gas analyzer.
Right. So you would have seen if there was any unburned fuel,
Yeah.
right?
And we have seen it when the combustor was not working. Right, we have seen
Right.
the fuel.
Fair enough. Okay, and the what about the water temperature? You guys cooling down the chamber to like with like water or something, or are you?
It's a water cooled. It's a water cooled system. Yes, so the combustor is water cooled. The idea is to in the next iteration reroute some of the inlet air around the combustor and recover that heat. Now it's going to the water, and it's now we measure something around 10% of the fuel power going into the water. We are expecting that to be, we can lower that because now basically the block, it's an aluminum block, water cooled, so it's basically cold. You can almost touch it. So
Yeah,
going
right.
into at least the stainless steel, we will reduce the temperature difference, so the heat transfer will go down, and we are also planning to add coating to the inner walls of the chamber to reduce also further that. And whatever is left, we will recover it by rerouting part of the inlet air around the combustor.
Yeah, fair enough. I mean, that's what I was going to say. What I pointed out in my work was that you lose I mean, you said 10%. That's surprising, but fair enough. That's what you measured. But yeah, about like a good amount, like in piston engine, just is lost to the wall. And but if you are you guys planning to sort of have a wall temperature measurement or something like that? Because you've mentioned with hydrogen having a hotspot technician. That
yeah,
surely
that's the next step, is to have a much better understanding of the whole temperature inside, and also understand how the different kind of operation change. So there is a pretty big difference between our system and the piston engine or your proper cost and volume chamber that you had the pre-prime. It's that the combustion time is really short, so the residence time, the gas is not there jumping, pushing against the wall, exchanging. So basically, when the pressure and temperature go up, there is an open outlet, so they tend to expand. So the flame propagation is very fast, and it very fast goes out from the chamber. So that I remember from one of your paper that the biggest amount of heat was coming out from the system during this time where everything was closed. So you had high gases at high temperature that were there just exchanging with the wall, and that was, I think, the biggest reason for the heat losses in your system.
Yeah, I mean that does answer the question. Yeah, no, it's very interesting work, Fabio.
Thank
awesome.
you. Very nice to hear from you.
Thanks for the answer.
Thank you, Quintan. So we still have space for any other questions you may have.
There is one in the chat, Nicolo.
Oh, thank you, Peter. So Judith Beta is asking you, Fabio, have you observed any issue related to thermoacoustic instabilities?
No, this is basically a controlled thermoacoustic instability. So we are generating an instabilities, but in a controlled way. So it's not, it's something different from, it's fights really much against what is the traditional way of designing a combustion system for gas turbine, when you definitely want to stay out from this kind of instabilities. But if you can control them and time them, then you can get an actual pressure wave that is controlled, and it's helping you to increase the gas turbine efficiency. I would put it in that way. So it's not really an issue for us, because we are generating it on purpose.
Thank you for the response, Fabio. I do not see further questions.
I would have one if we have time left.
Sure, yes, we do, Peter. Go ahead.
Yeah, I was wondering actually about the how do you manage the fuel injection? You have an inlet valve, I understand, for but this is only for sort of the already the combination of fuel and air, right? So you have a type of a what you would call a port injection system.
There is a port injection and a direct injection system. So it's basically two injectors derived from automotive industry, from piston engine. So you have the inlet injector. It's injecting fuel before the valves, and then fuel and air are mixed through the valve. And the direct injection, it's injecting directly in the chamber, and then it's using the swirl and tumble motion that you have generating, so the turbulence inside the chamber, to actually mix the fuel with the with the air, and that gives us the us the possibility of using one of the two for one fuel, and then adjusting the amount of fuel by increasing or decreasing the amount of hydrogen or methane that we are injecting from the different port.
Okay, and this is sort of also the means then these two fuel injection possibilities to then generate something like a staged combustion.
Yes, also that
behavior. Okay, understood. Yeah, good. And any indication or is there a general ratio of how much fuel is injected upstream in the port and how much directly?
It depends on the fuel blend. We have tested it. We basically can go all the way to 0 to 100. So we can inject everything from port and everything from direct injection. But it requires a bit of adjustment in timing. So we need to adjust a bit the frequency of operation or the timing that we are doing it to account for that.
Yeah, and it also depends a bit on the type of fuel.
Depends a bit on the type of fuel. So once you have decided what two fuels you want to run, you can map out your operation, and basically the control system will automatically change the timing of the system accordingly to what is the fuel blend that you're setting as an input.
Okay, good. Thanks.
Thank you for the question.
Thank you, Peter. Is there any further last questions?
Yes, I do have a question.
Okay, thank you very much. Aman, please
Hello,
go ahead.
everyone. My name is Aman. Hi, Fabio. I would like to ask you what is the best air to fuel ratio for attaining the maximum efficiency in a gas turbine? Because I come back from Camphil basically. So
the we can run this at different air fuel ratio. The best performance come with the richest fuel mixture. So the more fuel we can burn, the more pressure gain we can generate. So, but the limit it's basically given by what is the turbine inlet temperature. So for a combination of pressure ratio and turbine inlet temperature, we can predict more or less what is the pressure gain that we can generate. So the ideally the richer is the fuel mixture and their fuel mixture, and the better is the performance. But the limit is given by the turbine inlet temperature.
and should there be any kind of like temperature or mass flow of the air that is required for better efficiencies?
Sorry?
Is there any kind of temperature and mass flow ratio that plays a vital role in attaining better efficiency?
It's not really. I mean, it's for us. It's a given of the system. So what the condition that we have to fit in. So there isn't really a correlation between the things. I hope that I was clear enough in answering.
How to say? That's okay. Thank you, Fabio.